Okay, example 14-2, car springs again. Determine the period and frequency of the car in example 14-1A after hitting the bump. Assume the shock observers are the poor, so the car really oscillate up and down. So in order to solve this problem, we have to take a look back example 14-2, 14-1. So the 14-1, let me just read that problem for you. Car springs. When a family of 4 with a total mass of 200 kilogram step into their 1200 kilogram car, the car springs compress 3 centimeter. First question, what is the spring constant of the car springs? Assuming they act as a single spring. B, how far will the car lower if loaded with a 300 kilogram rather than 200 kilogram? So let me give you the condition of this problem first, and then I'll solve some of the 14-1 problem to solve the 14-2. So family mass, as I already mentioned, family mass, total mass. Family's total mass. Mass is 1200 kilogram, and the mass of the car is 1200 kilogram. So the total mass of the family and the car is 1400 kilogram. So the weight of this car with the family should be the mg, mass times gravitational constant, acceleration constant value. So that is mg. That is weight, which is 1400 kilogram times 9.8 meter per square second. That is 1960 Newton. So now we have to, so now the compression length is also one of the conditions. Compression length is 3 centimeter. From that, we can actually figure out the spring constant. The maximum compression length is 3 centimeter with this amount of force. So based on the Hooke's law, force of spring is the minus kx. Here k is spring constant, x is the displacement or deformation or compression of the spring. The minus sign only just indicator of direction of force, so you don't have to worry about it. So k value should be force divided by x, displacement of the spring. So the total amount of force applied to this spring is 1960 Newton, and that force create 3 centimeter displacement, so that is 3 times 10 to the minus 2 meter. From that, spring constant should be 6.5 times 10 to the 4 Newton per meter. So as you remember, period T is defined by 2 pi times square root mass over spring constant K for the simple harmonic oscillator with the spring. So that is the mass of family, and this is spring constant we this got from this Hooke's law. So if you plug numbers into this formula, then period should be 2 pi square root 1400 kilogram, and the 6.5 times 10 to the 4 Newton per meter. So from that, the period should be 0.9 seconds. All right. And as you know, the frequency is the inverse relationship with the period. So that is 1 over 0.92 second, which corresponds to 1.09 hertz. Okay. That's the answer for this example.